So yes, we can continue with the exercises or with the examples that I wrote. And let me go to the MD, QMM, NAMD, ORCA, right? And I will be also working in the corresponding folder for ORCA, right? So for these cases, I would prefer to work with the latest version of NAMD that we have installed. And I will purge and then load the modules for NAMD. For the QMM part, I will be working on the second section of the exercises. Yeah. So I'm assuming that you are sitting on this folder here, ORCA. And then I will ask you to open VMD. Then go to extensions, simulations, and QwikMD. Here in load simulation setup option, I will select the MDSim QwikMD file. And then open the file, and this will list several options, right? It says, do you want to include water, solvent ions, hydrogen, don't load hydrogen atoms? I won't check these options here. I will check the equilibration and then unselect initial structure. And I will choose load the last step, which will take the last step in the equilibration step, right? So it says now go to the QMM option, advanced run. We are already there. And for the protocol, which is that will be different now, I will go to, sorry, before that, I will go to QMMM in advanced run. Then, once I am in QMMM, I will go to protocol. And here in protocol, I will reduce the number of minimization steps to 3, annealing to 3, and equilibration 100 and QMM steps to 500. So this is just for teaching purposes, because for realistic systems, you need to go for higher values, of course. Now I will fold it up like this. If I don't do that in my local machine, for instance, this part is not well seen well. Then if I go to QM regions, I can click on plus here, and this will create a new QM region. Then I click on this line and it becomes blue. Then I will select the option, this in atoms, and this window will appear. And then in atom selection, this is a customized atom selection. And for this part, I will use a res name, which include GTP, a magnesium ion, yes, and another part which includes the residue of the protein. And this will be the sec name, which is called AP1, and the res ID 16, which is the residue close to GTP. So the solvent selection will be 0 because for this case, I don't want to include the solvent, just these molecules. But you can include them as well. And apply the changes. So it was fast, but if you return to that section, you will see that the total charge is -1, and the total number of atoms is 67, and this will be treated quantum mechanically. So this is an important feature that you need to consider. So from my attempts, I couldn't get a region that was not +1 or -1 in charge, right? Some other packages allow it, but a combination of NAMD and the quantum mechanical package doesn't seem to like that. So in your region, you need to include the residues and the molecules so that the total charge accounts for plus -1 or 0. Then you see that you have now a quantum mechanical region. I will follow it up this part. And then I go to QMM regions. And here, one needs to set the path of the program. There are some programs that are supported at this point. One of them is ORCA, and the other is MOPAC. MOPAC is for a semi-empirical calculation, as I mentioned before. That's a good starting point to explore your system. But for this case, we will use ORCA. And it says that the path hasn't been set at this point. And then I will click on this window here, and I will copy and paste the path to ORCA. And then open. And for the command line window, I will delete this part, the grid, and change this tight CF to no CS. So this is just one option. It's not that slow. It's just right, just to see that everything works. And you can choose your method here as you normally do with ORCA. This is the part for the basic set, and also the type of method that you want. In this case, this is a B3 leap functional. There is a question or a comment. It says permission denied to ORCA directory. So, well, I just copy this line here, and where it says set path, I pasted the path here. Okay, maybe you haven't set the confirmation message to our support team, right? That could be the reason. So in order to use ORCA, you need to send a confirmation message when you register to the ORCA software. Then you get a confirmation message. So you need to send that to the support email address. And then you will be part of the ORCA group at HPC2N. This is a requirement for the license type of ORCA. Then I will use the defaults in this, the other defaults in this part. And now we come to a simulation setup. So here, I will write the name of the file. Notice here that because I loaded the MD SimQ QwikMD file, this will recognize that name. But because I don't want the directory to be overwritten, then here I will rename it to, sorry, I will create a new file called QMSim and .QwikMD, right? And then finally, I will click on prepare. And it instructs me what frame or what snapshot do you want to use. I will choose the current frame, which was the last step in the simulation. So now it should be ready. So closed VMD. And then I will move to QM sim run. And you see that all these files were created automatically by QwikMD. So again, we will use a batch job to run the simulations, because if it were installed on our local machine, then we could click just on QwikMD button, and then it will use the ORCA installation locally. But because we cannot do that on the login node, we need to do that through the batch system. So I will try the minimization step and show you how it looks like. So basically, this is the MM part that we saw in the morning. These are the options for NAMD. Here we load the coordinates as the PSF file. temperature, the constraints, the thermostat and the barostat integrator, parameters, and in this part, the QMM simulation is turned on or off. So in this part, we say, yes, we want some part including the QMM part. So then we need a file, which is a PDB file. And here we can set some columns on the PDB file to be the atoms that are treated quantum mechanically, and also the atoms that needs to be treated as the boundary atoms, right? So in particular, in the beta column, we will tell the software, the NAMD, that we want these atoms to be treated quantum mechanically. And we can use also a different option to tell NAMD that some atoms will be the bonds. Here is the number of simultaneous simulations that can be run. And this is a feature that NAMD offers, where different parts of the protein not close to each other can be treated quantum mechanically. So that's why you can include more than one simulation, QMM simulation per node. So here there are other information. For instance, in this part, we tell NAMD that the column occupancy in the PDB file will be the one used for the information of the bonds in the QMM part. There is also one way to define the link atoms, but if you don't specify that, NAMD will treat the link atoms as pure hydrogen atoms, and this will be the default. There are other options, for instance, the bond scheme that you want to use, and how the charges will be distributed in the boundary atoms. Also, in order to avoid somehow the spilling out of the electronic density and to make the simulations more stable, you can use a switching function. There are some schemes in NAMD to treat the switching function. And also, you can tell NAMD how the point charges will be represented and how they will be treated by the QMM system. So this is the base directory, and you get this information directly from QwikMD. This is the part that I mentioned where you can modify the van der Waals parameters in case they don't fit your needs. And this is the electrostatic embedding, which is turned on in this case. There are more options that you can use, and all of them can be seen in the website of NAMD, and you can read how you can control more specifically your simulation. So there is one question in the chat. It says, I cannot load the MD's file. I'm running this, as you see, in the NAMD ORCA directory. And here I have the MD, SIMD, QwikMD file that we created in the morning. Notice that the name of this folder ends with ORCA, and we have a different folder for Gaussian. So let me know if you were able to read it, the QwikMD file, and I will continue with this website, which tells you more about how NAMD controls the QMM part. So you see, when the flag QMM elect embed is on, then you can choose electrostatic embedding and the mechanical embedding. And this is not that precise and not accurate, but could be good just for giving you an idea of how your system behaves. Then you can apply a switching function, as I said, to make your simulations more stable and avoid some potential electron leaking. But this is just one approach. It's not, doesn't completely solve the situation. There are also some schemes for switching, and the point charge scheme can be treated in different ways, because sometimes the charge in the QM region and the charge in the MM region doesn't add to 0 or to an integer number. And this can be handled by these different schemes here, where you can round off the charges. Also, you can treat the link atoms by using either a hydrogen or some atom that you want. There are also schemes to deal with the point charges, right? You can simply ignore what happens or keep the total dipole moments and so on. And in the custom chemistry software, we can see that NAMD and VMD work natively with ORCA and MOPAC, but the Python script feature can be used for other packages, like for instance, Gaussian, TerraChem, and QChem, and this is the one that we will use as well. Independent regions, as I said, maybe you have one binding site in your protein, and you have one allosteric site, allosteric region, and you want to model them in the same simulation. That's possible with NAMD because it can handle the independent QM regions. So I would recommend you read this page to fine-tune your simulation. Good. The person could copy the files. That's great. Okay, so now let me continue with this simulation for ORCA. And I'm now in the QMMSIM run folder, and there are some configuration files. We have seen this QMMmin, the .conf, and the different options. The software for this case will be ORCA, right? And this is the path that we set in the window for the QwikMD. So I just took it and copied that here. The Mulliken charges will be used. They are very simple and straightforward to compute. So notice here that for some reason, in this case, QwikMD didn't use the options that I passed. So it used grid 4, and I won't use this grid 4. And also, it is using the type SCF, but I wanted the non-SCS. Yeah, because this should be faster, I think. And just after this line, I will add the following command: config line, and then pal and proc. And by adding this line, I will be requesting 10 cores for the ORCA simulation, right? In addition to this, that's it. So if you need to use less than this number of cores, then the option is different. It's not PPAL, right? I will recommend you look at the parallelization website for ORCA, and they will tell you what option you can use if less than, I remember, 4 cores are used. So now let me copy the NAMD QMM SH file to this folder, right? And I will inspect this folder, and I need to correct the project. This is SNIC. And we are using today a reservation. Yeah. Okay, so there are some differences in this script with respect to the one that we use for the NAMD. So notice here that ORCA can be used with the no MPI version of NAMD, which is a threaded version. It's not the MPI one. And for the purposes of teaching, because it takes some time, I will be running only the minimization step with 3 steps. In addition to this, notice that I'm using 14 cores but only 4 will be used by NAMD here. And the rest of them, the 10 other cores, will be used by ORCA. And that's why we set here MPROC 10, right? So if for some reason you request here 10 and you use 10 for ORCA, you will get an error because ORCA and NAMD use different cores for the simulation. So you need to tweak these values. Okay, that's it. And then I can submit. It's running and I can check again how the simulation behaves. So it takes some time. So in the meanwhile, I will check what happens here. So I have an output file and this will tell me what is happening. So maybe it worked, maybe it didn't. So it seems that the simulation is running. And here you can see if the total amount of cores that you requested are being used or not. So let me go to the folder called exec. And then minimization. And here inside this folder, exec minimization, there is a folder called 0. And here there are the folder, the files generated by ORCA. And at some point, so you see from the 14 cores that I requested, I using about 91%. So in this folder, I can see some information from ORCA. And it is telling you how the simulation is going. So it's computing exchange correlation gradient. And so at some point, yeah, it starts the self-consistent field procedure that was mentioned in my talk. And then so it starts the iterations. And only when it converges, it passes the gradients and the energies to NAMD. In the case, of course, if that converges. It could be that the initial geometry that you provided is not that good, and you need to somehow treat it manually or by using your chemical intuition or some other quantum mechanical package. And that's why I suggested first to use a semi-empirical method, maybe to get a guess geometry, and then one could use a more accurate method. So ORCA is doing now the self-consistent field procedure. And NAMD is still waiting for the ORCA information. So just the first step, the energy calculation has been computed. I see here you can see something at some point when ORCA is running and both are running, then you see almost all the resources being used. But when just NAMD is running, then just the 4 cores are used and so on. So, but unfortunately, they cannot work together because they are separate software, right? Which is good because then 2 completely disjoint communities can work together. Notice also here that one step in molecular dynamics can be computed quicker, but here we have performed just one step and it's taking a lot of time, right? So the bottleneck in these simulations is not the molecular mechanics package, but it's the quantum mechanical part. And that's why also quite software like Charm are very good for running QMM simulations because of although the Charm MM part is not that fast, the QMM part together with the MM part work very well. And because the QM part is the bottleneck, then it doesn't matter how fast the MM part is. Yeah? So this is just the first step. Is there any questions at this point? I don't have an example right now on how to use Amber and Gaussian. I need to explore that actually. That's for sure. Amber, it's another package that has a very good interface for quantum chemistry packages like Gaussian. Also, Amber has a quite good set of tools for dealing with semi-empirical models. And it's also well optimized for that. There is a question for long side chains like lysine. Where would you suggest to cut the C beta, or is it still okay to cut closer to NH3 plus? So it depends on what is the reaction. And for instance, I would say if the lysis that you want to include is not the one that it's taking part in the actual reaction, then cutting just the terminal group at that level, that would be enough, right? But to make the simulation more stable, if the lysine is taking part in the reaction, then I will suggest to cut it at the level of the C alpha atom. Because also one needs to consider the size of the simulation, right? Because including all the atoms in the lysine, especially if you have many long residues in the binding site, that could create a big quantum mechanical region, and that will make your calculation slower. But I will suggest that if this residue is not taking part in the reaction, then one could try to cut it at the level of just the terminal group only, and check the results, how they look like, right? And also, what can I say? QMM simulations have evolved because, as I said before, I remember that when one tried to set up a simulation, one needed to do some file editing manually, right? And do the stuff manually, for instance, with Charm or Amber. But now there are more tools. But even in that case, the QMM simulation haven't reached the point as in the classical MD with Charm GUI, for instance, where you just put the parameters in an interface and then you get the output files. That's not the case. One needs to apply the chemical intuition and see how do one simulation and then check how it is going, if that matches the chemistry knowledge that one has, and if that is not doing something very unrealistic, right? So we need to check back and forth, so to speak. So the simulation has finished for this part, and then we can visualize the trajectory as we did before. Let me see. Oh, there is a question how to use a reservation compute time for the present course. I mentioned that the reservation is QMM-course. But in general, you cannot do that for individual usage. This is done just for the course. One cannot reserve computing nodes for doing other tasks. You need to go to the regular queue.
I also put it in the important information page, how to use it during the course, but also that it is only during the course.
It's only
So,
during the course.
yeah. Yeah, so it is, you can find it there as well if you want.
Yes, this software, Amber, it's also very useful, and I will consider that in future courses, I think. So is there any further questions or on this setup? So the simulation finished, and just 3 steps were computed in about 12 minutes. So that's a lot, right? And you saw before that the results are written in the folder QMMX, and these are the steps. We run only 3 steps of minimization. We haven't done these steps, right? But in a realistic system, yes, you need to do them. So basically, in this example, we were treating residues and GTP and magnesium quantum mechanically. But if you want to study chemical reaction with the transfer of some group, then you need to set some free energy calculation, as I mentioned before, right? For instance, here is one reaction that I studied previously. And this is for the transfer of a phosphorus group in an enzyme called QwikMD kinase. So these are the important the important parts of the molecule. So I can put it here. So here, let me as I did before, I will align the frames so that they look in the proper orientation, all of them. So here, notice that I started a reaction with two molecules, ADP, S3P, yes, and one magnesium ion and some coordination waters that are not displayed here. And during the course of the reaction, this phosphoryl group will be transferred to this other molecule, like this, right? And this is the goal of the quantum chemical method. This part and some residues, including some lysines and arginines, are treated quantum mechanically. But in the present case, I didn't set the different windows for the free energy calculations. In NAMB, one can use the so-called EABF method. I wrote it on the chat, which is a type of ensemble method. And this can be in conjunction with the type of simulations that we have seen today. But this requires more time, and I haven't said it up to this point.